Alright, so today we're going to be talking about the modified Atwood oscillator post-lab. So thus far in Unit 4, we learned that an object with a certain velocity will remain at that same velocity unless acted upon by a net force. In other words, we know that the forces acting on an object are balanced if the object moves with a constant velocity. This is also called Newton's first law, or Newton's law of inertia. On the other hand, we were also able to tell that if a system is accelerating, like in the hovercraft pre-lab, we knew that Mr. Scheffler had to push me in order to get the hovercraft going. So if the system's accelerating, we know that it was experiencing a net force, or in other words, the forces were unbalanced. We know that if something's accelerating, it obviously has an acceleration, it has a mass, and therefore it also has a net force acting upon it. We can do one of three experiments, basically looking into two of the three things and doing a round robin between acceleration, net force, and mass. So we did the first two because the third one is honestly very difficult to set up in the lab. So we did acceleration versus net force and acceleration versus the system mass. So in our two investigations, we were studying acceleration versus net force and acceleration versus system mass for the modified Atwood oscillator. One thing that we had to talk about beforehand was the effect of a pulley on a system, and note that all a pulley really does is it bends an axis. So in this case, our usual x-axis starts horizontally, and because of the pulley, we want our axis to be in line with the string. All right, so here's a string, so we want to make sure that the x-axis bends along this way. So in our pre-lab discussion, we talked about the forces acting on the system. If we were to define the system as the carts, the string, and the hanger that was falling. And what we did then was we created a force diagram for the forces acting on the system. Now, real rough, we know that there's a force of gravity acting this way in the positive x direction. So there's this force of gravity, and there's also this force of gravity. And there's also a normal force acting on the cart. Okay, now making a more formal force diagram, what we have here is in the y direction. Now this is from the perspective of cart 1, anything sitting on the table. We have Fg on M1 by Earth. We have the normal force on M1 by the table. It's actually a track. And we know that these forces are balanced because the system is not accelerating in the y direction. However, it was accelerating in the x direction due to the force of gravity on M2. Okay, so what we do know is that this is the reason that the system was accelerating. So it was the net force. So in the first investigation, we were curious about how adding more mass to only M2, because we wanted to increase the net force, we added only mass to M2 by taking mass from cart 1. How did that affect the acceleration? In the second investigation, our system remained the same, and our force diagram remained the same. However, what we did do was we increased the system's mass by adding more mass only to cart 1. And we wanted to ask the question, how is increasing the mass on M1 by introducing outside masses affecting the system's acceleration. After we graphed our data, we found that the acceleration versus the net force yielded a straight line, so these are directly proportional. However, acceleration versus system mass yielded a hyperbola for our second investigation, so we knew that they were inversely related. After straightening out the ladder graph, we were able to straighten out the acceleration versus the 1 over system mass graph to give us a straight line. So we knew that from the first investigation, acceleration was equal to some slope times the net force. And then we also knew from the second investigation that acceleration is equal to some slope times 1 over the system mass. Remember, we had to straighten it from being a hyperbola. After comparing our numbers as a class, we found that the reciprocal of the system mass that I told you to write down and to keep constant from the first investigation was the slope. And also from the second investigation, the net force was just the FG on M2 by Earth that I asked you to keep constant because we kept the hanger mass constant. And we learned that for an accelerating system, acceleration equals the net force divided by the system mass. And it's most commonly written as this. Net force is equal to the system's mass times the system's acceleration, otherwise known as Newton's second law of motion. And that was our post lab. Also, I'll see you in class.